Hello, can you hear me?
Yes.
Okay. Okay.
Hear you.
Okay. So are the slides already visible on the screen? Okay, I see them now. Perfect. So thank you very much to Kotlin London and all the organizers for letting me be here today. It's a big pleasure. I really wanted to be part of this event last year, but it was almost impossible for me. So happy to be here finally and to have this chance. Thanks for inviting me. Thanks to all the people watching. I'm Jorge Castillo. I'm an Android and Kotlin Google developer expert, and I'm part of 47 Degrees. I'm one of the parts of the pieces of the 47 Degrees Academy, which is the platform we use for teaching people, developers around the world about functional programming, and also not only functional, but platforms like backend, mobile, and much more. So if you're interested, feel free to browse the website in the 47 Degrees site. And that's pretty much it. We are going to talk about functional Android today. So it's functional programming applied to the Android platform. So we will go over like a lot of different concepts we find in the functional world applied to this platform. So let's go already to the content. The first question I will make myself before picking a new paradigm is basically why. So why functional programming? And what it is. When I personally think about functional programming, I think about determinism. So it's one of the ultimate goals of the paradigm to try to achieve determinism over our code bases to make them more predictable, easier to reason about, and also easier to test, obviously. So the paradigm is going to help us on that. And that obviously means that we are not going to be very friendly to side effects, right? So side effects are always present because Android is basically an effectful platform. We need to show the stuff on a screen. We need to query network. We need to query databases, read from files, and so on. So, I mean, the side effects are going to be there, but we want to get them under control. Okay, so that's going to be like the ultimate goal of all this. So it's not so much about getting rid of the side effects, but more like getting those under control. So another very interesting thing is the concern separation. And concern separation is something that is really present in the functional world, but not only in the functional world and functional APIs, but also on many other APIs in different platforms and libraries out there. So it's this idea of having the chance of kind of writing our program, we could say declaratively. So what you are creating is more like a description of a program, and then you have the chance to consume the program later on. And that's where you decide how you want to consume the program. So there is this differentiation between what we usually call the algebras in the functional world, which is basically our pure functional logics. So the logic of our program. And then the actual runtime. The runtime is the moment where we finally or ultimately execute or consume the program, right? And that's really important because that gives us the ability to reason about how the program is written before consuming it. And we can then, therefore, apply different optimization mechanisms or, decide how we want to consume it. In the world of Kotlin, you can find Kotlin sequences, which is actually using this concept, right? Because they provide you these lazy operators that allow you to compose the logic of your program, or at least the logic that is going to be working with the sequence in a kind of lazy way or declarative way. So all that code is not going to be executed until you decide to consume it in the end. So there are some terminal operators in the end, which are the ones in charge of actually consuming it, right? So before that point, everything we could say stays like cold, maybe we could call it. And declarative, it's more like a description of our program, but then you have a terminal operator to decide how you want to consume all that program. And at that moment, I think it's really interesting because that's the moment where we can not only pick how you consume it, but and finally execute the whole thing, but also maybe apply optimizations like decide, I don't know, since you have like the whole picture in memory of how the program looks, at that point, you can decide if you want to skip different parts of it because they are redundant, or maybe you want to offload different parts of it to different threads or contexts, or even parallelize the execution of different computations that compose that program, right? So in that sense, having this concern separation gives us the ability to have the program in memory first and to see the big picture and then decide how efficient we want to be consuming it also. But we can also find it in the world of Android. So Jetpack Compose is also using this idea. Compose is a pretty new platform, but if you dig a little bit into the sources, you'll probably find out at some point that they are kind of having this slot table, which is like a representation of how the UI looks at any point in time in memory. So what they have is like an in-memory table or a structure that is holding all that information and metadata that is able to represent a given state of our UI at any point in time. So just by looking at the slot table, the library is able to later on interpret or consume that slot table and materialize actual and real UI from it. So in that sense, they also have this idea of concern separation, because based on what's on the slot table or that in-memory structure at any point in time, they can also apply optimizations like things like smart recompositions for skipping recompositions when the data you need is already stored in the table, so you can just grab it from there and things like that. So also ideas like parallelizing compositions and things like that that might be coming in the future, even if they are not possible now. But overall, they are kind of leveraging this idea of concern separation also, even if that's only for them within the library. It's not something you can make use of it as a client at this point. So I wanted you to peek a little bit into the composable functions, because they have a lot to do with suspend functions, or are really similar to the suspend functions. And those are, the later are going to be really important in the world of how we flag side effects in functional programming. So I want to go over both types and compare them a little bit. So composable functions, we can say that they describe an effect. It's a function that describes how the UI is going to look whenever it gets displayed or rendered, we could say. But it's more like a description of that. It's not yielding actual UI when you execute it. What they ultimately do is emit changes over the slot table. So there is a little bit more complexity there, but you can understand that the actual composable function is not defining or creating a view, but defining how the view will look like. Not the view, but the UI component, we could say, will look like whenever it's finally materialized. So it's more like a UI effect, we could say. But the cool point here is that they are not callable from anywhere. You can only call a composable function from another composable function, or the integration point, right? Which is the set content call, where you're going to fit all your composable logics. So in that sense, they create this restriction that kind of crawls up your call stack, because if you flag a function as composable, then you can only call it from another composable function, and that one can only be called from another composable function. So it's like a requirement that will keep crawling up your call stack until this entry point of your program, that is the integration point with the platform, we could say. Obviously, that's giving them, the team, the certainty that it's all gonna be like a composable function call stack, one after another, so they can ensure that they cannot take the compiler and replace all those functions in the call stack by new versions of them that automatically pass this composer implicit parameter. So in that sense, they just want to ensure that context all the way, so they can pass the composer around across all those calls, and that's what will ultimately drive the composition and how Compose library works. Another cool point of composable functions is obviously that they are compile time tracked. So this is the same thing again. You cannot really call them from anywhere. The compiler will not really allow you to compile when you are trying to call them from wherever, but only when you are calling them from another composable function, right? So this is basically as flagging UI effects, so the compiler is aware of those. So the compiler is already giving us feedback about how we call those effects and from where we call those effects. So that's giving you a lot of safety of how you're using or calling your effects at compile time. So that improves a lot the feedback loop and makes sure, be sure that you are using them correctly. In the world of suspend, we have the same idea. So they almost map one-to-one between each other. So the suspend functions are also describing an effect. In this case, it's any type of effect, not necessarily a UI effect, which can also be. They also impose this calling context restriction that is going to crawl up the call stack, because if you flag a function as suspend, the compiler will make sure that you cannot really call it from anywhere. So you are only able to call this suspended effect from other suspended context, another suspended function, or a coroutine, which would be like the integration point in this case. That makes sure that what you have is a suspended call stack all the way edge to edge, and that makes sure that the calling compiler can basically implicitly pass this continuation parameter across all those calls, right? And that's what drives how coroutines work in the Kotlin runtime. So the compiler is, again, keeping track of those effects. It's the one that is going to decide where you can call a side effect and where you are not allowed to call it. So it's basically the same idea. So we could say that they are reusing, in Google, they are reusing the same idea of suspend, but for a different ultimate goal, we could say, in the case of composable functions, right? But this is really important because suspend functions are, because of this, a really good way to flag side effects, because that's going to make the compiler aware of what is a side effect and how you are calling it in your code base. So let's start using it in our favor. Let's start flagging our effects as suspend. Let's imagine we have a few, I don't know, network service, a network service, a persistence database, and then an analytics tracker, for example, so or whatever. So you can imagine any type of side effects that you can have in your program, you could flag them with suspend, and that's automatically going to tell the compiler that you cannot really call them from anywhere. You're adding this restriction, which is really important because that's giving us and the compiler certainty about how the side effects are used in our program. But obviously, we are going to need a runtime, right? As we were saying, we impose this calling context. So at some point, there is this integration point we will need for running our suspended code base inside. So we are going to need to create a coroutine. In the world of Kotlin X coroutines, this runtime for our suspended program, or this environment for our suspended program, is basically created using the coroutine builders that you can call over a coroutine scope, and you can make use of the structured concurrency and all that. So you can invoke, create these child jobs and all that kind of stuff. So you're using Kotlin X coroutines, you could basically put your suspended program in there. That's the integration point in this case. That is interesting, and Arrow, the Arrow functional library in Kotlin, is providing a lot of functional operators that will work seamlessly on integration with Kotlin X coroutines, starting on version 0.12. So we are going to provide direct integration with Kotlin X because it makes a lot of sense, given it's a library that is obviously everywhere. So it doesn't make a lot of sense to fight against it, but instead provide good means for integrating both of them together. If you are still on 0.11 or older versions of Arrow, you have the environment also. I mean, you can create an environment by yourself, which is what Arrow provides to create this kind of a safe environment or environment prepared to run suspended programs. So the environment will give you the ability to pick how you consume the suspended program. So we are talking about concern separation again, right? The environment will give you the ability to pick how you consume it in terms of whether you want to do it in a blocking way or non-blocking way, or if it's going to be sync or async or cancelable. You pick the execution strategy with it. Also, you can pick the context for what you want to use for running the program. And yeah, you can put your program in there and run it. This, for example, is the async cancelable execution strategy that gives us a disposable that then we can invoke later on whenever we are ready to cancel the whole execution tree, right? So all the child jobs that are created hanging from this kind of root element, which would be the environment, are going to get canceled. So that is how you can do it with 0.11 in arrow. But as I say starting on 0.12 and ahead, you are going to have the chance to integrate it directly with the coroutine builders and Kotlin's coroutine. So it's going to be much easier for you to integrate it in the code bases where you are already using Kotlin most likely. So the runtime picks the execution strategy. As I was saying, it picks the context for on what to run the actual suspended program, or where you want to consume the suspended program. And it also has the chance to apply optimizations when consuming the program. Cool. So about the entry points, there is always like an entry point to a program. In the world of Android, we don't have like a main function to run our app, but it's more like we are given these callbacks in the fragments and activities life cycle. So we need to fit also the views. So we need to fit our logics in there on those callbacks. So those entry points are definitely not suspended. And in that sense, we are going to need to create a coroutine by ourselves to run our suspended program in there, right? So in that sense, in Android, you will be enforced to either use the coroutine builders or use the arrows environment. But you need a means for creating this environment or runtime that is essentially prepared to run or to consume suspended programs inside. If we were using another platform like backend, and maybe we are using Spring or Cater, some of these platforms provide you the ability to create suspended entry points. So you have the chance to declare your endpoints as suspend functions, which basically is giving you this environment already built in or right out of the box. So you don't need to create the coroutine by yourself. You can just go ahead and put all your suspended logics in there. But in the world of Android, that's not going to be the case. So, well, we have this idea of concern separation. We know that we want to use the suspend keyword for flagging our effects. We know that we have our this sense on the requirement that we will be imposing by using suspend. So that will crawl up all our call stack. And at some point, we will need to create the coroutine for running all that suspended code. So that's going to be the entry point. We have this idea. So we have the entry point. We have a way to flag side effects, to keep them pure by using suspend with this requirement. But we have still not looked on, to how to encode the actual logics of our program. So the data types are going to have a lot of, importance here. Because data types basically are used for wrapping our data, and then they raise a concern over our data. So we will be using different data types, but either is going to be a very common one, and you will see in a second how it works. But it's based on this idea of railway-oriented programming. So we are talking about programs that have two rails, right? If we think about any program out there, any computation in a program, it can always go well or wrong. So it either succeeds or fails. And you can represent that as a couple of rails that your computation might follow, right? So you can think about your function, something like this, right? You have a function f that might potentially succeed or might fail, right? So you have two possible rails, two possible paths that the execution could take. That's called, you can think about programs in that way as a composition of functions that might fail or succeed. And that's called railway-oriented programming. It's a concept created, I think, or defined by Scott Woleskin back in 2013. So it's a pretty old concept, still very, very, it still applies, it still makes sense. And there is this talk and this post that I'm probably going to share later on, I don't know, on Twitter or somewhere. So you can also click on it. It's very interesting for digging a little bit more on this concept. So either is going to be a big player here in the world of functional code bases, and it will give us this kind of duality for our computation. So there's always going to be a path we want to follow versus an alternative path. happy path versus the error path, we could say. In the world of Android, it is going to be exactly the same. Any computation might go well. It might succeed or fail. And the happy path is likely the one we want to compute over, where we assume that everything went all right, we were able to retrieve the information we were looking for and all that kind of stuff. So we can keep computing over it. So that's the happy path. In either, that's going to be the right side, and but you will see it in a second. And the left side will contain the errors, which is going to be like this alternative path we don't like that much. But either will make it explicit that the computation might either succeed or fail. So this is all about making that duality or disjunction explicit all the time. So whenever you are going to process a result that is wrapped into either, you are always going to be enforced to think about this duality, and maybe also enforced to handle both sides, so you don't forget about any of those. Okay? So this is either, it's obviously an intentional oversimplification, but you see how it's a sealed class with two possible implementations, left and right. Left is going to contain a value of type A, right is going to contain a value of type B. We can assume that right will always contain data, and left is where we are going to put all our errors by convention. And then you have map, flat map, all that kind of operators that we are familiar with already, most likely. So fold is an interesting operator that you have that basically gives you the ability to handle both sides, because you never know if the either is going to be a right or a left at any point in time. You need to check for the type, and fold is basically doing that. It's like a when statement that allows you to pass lambdas for both sides. So depending on the side it is at this point at a runtime, if it's a right or a left, it will run one lambda or the other, right? For example, here we load a user. Let's say that goes to network and returns a valid user. In this case, we are mocking the result. It's going to be a right wrapping the user because it succeeded. So we use right to reflect that. We wrap our data into right, and then we can fold over it to the side what to do with it. In this case, this is the lambda that will run. The other one will not run because it's a right. Okay, so we can render the user in this case. So fold is cool because it's basically how you apply side effects over an either instance, right? It's providing you the ability to handle both sides. For nullable data, option is a good option, no pun intended, but option is still usable, but it's getting demoted in Arrow because option is kind of colliding with in Kotlin with the nullable or the question mark modifier or the Kotlin nullable types. So in that sense, most of the time, they are reflecting the same thing. It's basically the presence or absence of a value. They are raising the same concern, we can say. So in that sense, we are always going to recommend going for the more idiomatic solution here, which is the Kotlin nullable or nullability support. But if you still want to use this kind of monadic style, either is also going to support nullable types. So in that sense, you can use from nullable, which is basically this constructor function that you can call over the companion object that will allow you to pass any nullable value and will return you an either right if the value was found or an either left of unit if the value was not found. And then you can, for example, ally unit to a more strongly typed domain error that you like, okay? Like episode not found or whatever, to be a little bit more semantic, because unit is probably not very explanative or descriptive, okay? Other than that, I mean, you are using either the same way you would use option. You have a map, flat map, and so on, so you can basically keep computing over your data or over the error, you can transform it, and things like that. Why not to use option? Because it's a little bit redundant having the Kotlin nullable types. So we are gonna try to promote the most direct possible style, which is the one using Kotlin nullability support. Okay. Still, we are going to keep option around. Option is going to be probably moved to a different package because there's a lot of people obviously using it, and there are some libraries like RxJava and other libraries that are not really good friends of null null types. So in that sense, option is still going to be there if you want to use it. But I can say that for all the cases where you were using option, you can also use either, because at the end of the day, it's a disjunction. Instead of present versus absent, is left versus right. So you can basically define the same use cases you've been defining for option using either. So you can, if you want to go for either, you can also use either for that. Okay. Okay. This is going to be very important, because in Android, we use third-party libraries all the way. Like, I don't know, let's say that you are using Retrofit, you are making a network query, or you are querying a database using Room or whatever. So you have a suspend function that represents your effect, your side effect, and you want to integrate that with either, because you want to reflect the result of that operation. You want to wrap it into either, right? So in that sense, you have either catch. Either catch is an operator in either, which we could understand also as a constructor, because it's a function defined over the companion object that allows us to pass any suspended effect to it. So in that sense, you can use it to wrap the result of any suspended effect. It will automatically wrap the result into either right if it goes well, or into either left if it throws an exception. So in case it's an error, it throws, you will get it into either left, that exception, okay? So it'll be left containing that exception. And if it succeeds, as I was saying, it's going to be right containing the actual value. Then you can use map left, which is really handy for integration with third parties, because it gives you the ability to map the throwable into something else. So you can map your throwables into strongly typed domain errors, which is also really common in Android, because we don't really we are not very used to work with exceptions right away, but we prefer to map them to strongly typed domain errors as soon as they enter our domain. So it makes sense to use map left, in my opinion, for that. Okay, like in this example. So basically, with these lines, you can integrate the either data type with any third-party call, as long as you reflect that as a side effect using suspend, which is what we are suggesting to do. Okay. Okay, there you go. For composing logics, because we already got means for flagging effects with suspend, we got means for the entry point for consuming the actual suspended logics in our program, in this case in our apps. So probably the only missing piece would be how to compose the different logics. We are using either, most likely, at least so far in the presentation. So we can just map or flag map, use like the standard combinators, we could say, or operators for chaining calls on top of either, or for chaining another either value on top of the initial one, and compose computations using that data type. How does flag map work for either? That's very important also. Well, flag map is basically for sequential operations, okay? In any data type out there where you use flag map, is basically for chaining computations over that data type. So in the case of either, it's just the same. You can have two dependent computations where the second one depends on the result of the first one. So if the first one succeeds, the second one will be able to be performed without any problem and might succeed also. But what happens if the first one fails? Well, in that case, you cannot really perform the second one because you don't have a successful result on the first one, which was a requirement to perform the second one, because both computations are dependent on each other. Not on each other, but the second one depends on the result of the first one. So you cannot ever execute it if you don't have a successful result in the first one, right? So in that sense, you can just skip it. It's some computational time that you are saving because there is no way for you to actually run it. So that's actually called failing fast, or error short-circuiting. So in this case, what either does, and if you have your computation, your program as a composition of eithers, you're going to be using flag map. And in that sense, flag map will basically forward the error. If it gets an error as an entry, so it's going to be a left containing an exception or an error. If you flag map over a left, it will just return the same error into left one more time. So it's not going to do anything with it. That is why we say, and also the same thing for map. So we can say that the operators that are meant to work over the happy case or the happy side of either, like map or flat map, those are right biased. So they are only going to apply their computation in case it's a right. Otherwise, if you are not on the happy path, if you are not computing over data, but you are processing an error, they are just not going to perform that computation, but just forward the error as is. Okay, so in that sense, effectively, that means that as soon as you get an error when you're chaining computations using either flat map, that's the other error you are going to get as the result of the overall composed computation, because it will keep forwarding the error right until the end, as soon as it gets the first error in the chain, right? And that makes sense, because if we are talking about sequential computations, you cannot really keep computing if a previous computation fails. You don't have your requirements, you cannot keep computing, so you can just short-circuit the computation and return the initial error right until the end, right, as the result of the overall composed computation. So flat map works like this. You can, this is very standard, but you can have, for example, a couple of effects using suspend. So they are flagged as side effects. So load speaker takes a speaker ID and returns either an error or the actual speaker. This is it's mocked, so you have an idea of how it looks. This another suspended effect also takes like a list of talk IDs, and in this case we want to load a list of a collection of talks by their IDs, so it can either return an error or the actual talks in case it succeeds. So for flat mapping, you just make the first request and then you can flat map and perform the second request. So you can see how we are using flat map as a means for chaining a couple of operations or computations that return either in this case, right? The second one is using the result of the previous one to perform each job. So obviously this is a computation that we would never be able to perform if the first one failed. So if the first one returns a left with an error, you cannot keep computing, and the overall composed expression will return left containing that error or that exception. In this case, it's going to be a speaker not found error. Okay, that's the error side on the initial computation. So we short-circuit the computation, we forward the error as is, and it's going to be the result of the overall composed computation. If we are talking about sequential computations, there is also this alternative style, which is either bindings, where you can create an either computational block, we can call it. It's like saying, okay, I'm going to compute with either all the way. I have a bunch of operations that are using either, and I want to run sequentially. So what I do is opening this either block, and then you can use these bindings inside. So you perform the initial computation and you bind over it. And binding it means that you have the inner value for the happy case available right away in that line. So you can assign it to a variable on the left-hand side, for example. So you don't need to explicitly unwrap it. You have access to the inner value already. Remember that this returned either. So if we don't bind, what you will have here is an either. But with the power of bind, we give you the ability to access the inner value only for the happy case. So you can use it right away in the next line without any sort of callback style or nested style, right? You can use it in a more direct style. So you perform the second operation, and you can also bind to access the inner value right away on that as a result, instead of the wrapped value into either, okay? So that's really cool. Maybe not, probably not really big improvement in this case, because we only had like a couple of computations, and it might be simpler to just use flat map, because this is flat map under the hood. The arrow compiler plugins or annotation processors are basically translating this to a chain of flat maps. So it's just basically the same than this, right? But in this sense, if we only have a couple of computations, it's probably simpler to go with the standard flat map style. But it gets more powerful when you start having more computations, like in this case, right? The more computations you have, you start feeling that this style allows you to have like a single level of indentation and a more direct style where you work more like synchronously, we could say, instead of using this nested or callback style that you get with flat map. So in this case, let's say we have the initial operation for loading the speaker, another one for loading the talks, taking the talk IDs from the speaker that we have just loaded from network, and then another one for loading the event details for the event of each one of those talks. Okay, so overall we have 3 sequential computations that we want to sequence, to chain. All of them are returning either. So again, we can use this either block and use bind, right, on each one of those. So we get access to the inner value right away in the left-hand side for each one of those. And you can encode the whole program, which in this case is chaining 3 different computations that return either, but with a single level of indentation, or a very sync-like style, we could say. So about failing fast or short-circuiting, this is something we mentioned. What happens if you get an error on the, for example, on the initial computation? So what you get is a left of a speaker not found. That is an error already. So that's basically moving us out from the happy path to the left side, to the error side. So that's going to short-circuit the whole computation. It will just not perform this computation, neither this computation, but just return left of a speaker not found as the resulting value of the overall block. Okay, so it basically short-circuits the whole thing. It doesn't compute further, and returns that initial error as the error as the result of the overall computation. Cool. So if we think about programs, I mean, we think about programs out there many times, or the big majority of the time, you can think about those as a composition of functions that might succeed or fail. So in that sense, you can reflect any programs as a composition of computations or functions that return either. But in that case, we are talking about sequential computations, as we've been saying. So computation always depends on the result of the previous one. And ultimately, any programs are basically a sequence of computations, right? Because you have a computation, you have an operation that maybe goes to network. In Android, right, if we focus in Android, maybe you are going to network and then you want to map the errors, and then on top of it, you flat map because you want to apply another computation on top of that data. And you keep mapping and flat mapping all the way, depending on the amount of layers you have. But at the end of the day, you're going to have like a chain of either's, right? So in that sense, you can reflect any call stack or any logic in Android using the either data type, most likely, unless you want to go for something like streams or something that we are also going to cover today. Then you will need a different data type. But in the case of one-time or one-shot calls, either is more than enough in combination with suspend, right? Because that's what it's going to give you the safety versus side effects. But what happens if you want to accumulate errors, right? When you are running independent computations, that doesn't make any sense, because if you get an error in the initial computation, you cannot really perform the second one or the next one in the chain. So there is not such a scenario where you have many different errors, because the first one is the one that you are going to keep. But in the context of non-dependent computations, like for example parallel operations, you could actually be interested in all the errors, like gathering all the errors for, I don't know, if you're, in the case of Android, you want to gather all the errors for validating a form or something and show feedback to the user all at once, instead of giving feedback for each one of the, like validating each one of the fields separately, calling the server, getting the result, giving feedback to the user, like field by field. That's not ideal. What you prefer is obviously validating everything all together and provide all the errors together to the user. So in that case, you want to perform all those operations independently, potentially in parallel also, maybe, and gather results in the end, and also gather all the errors in the end in case there are one or many errors. So either is not great for that, it's not defined for that, and for that you have validated, which is a different data type. If you remember, we've been saying that data types raise a concern over the data. In the case of either, it raises a concern of the data being success or fail. So you have this duality. And in the case of validated, it's more like valid versus invalid. That's what it's raising. And validated provides us this type alias, which is validated nil, which stands for validated non-empty list, which is the one that is able to accumulate errors. So that is the same as validated of a non-empty list of errors or the actual valid result in case it's valid, right? So in the case we have an error, we always need to have at least one error, and it's able to support a list of them. Okay, that's why it's able to accumulate the errors. And we also have operators here for mapping and flag mapping and all that. I'm just simplifying it here so you have an idea of how it looks structurally. So here is an example of how you can use validated NEL for error accumulation. Let's say we have another couple of effects, okay? One is for loading the speaker by ID. In this case, we return validated NEL. That's the concern we are raising. In the case there is one or many errors, we are going to map all of them to speaker not found, a single type. Otherwise, we are going to get the actual speaker. So, well, we can go like, okay, validated catch NEL. If you remember, we were using either catch before for integration with third parties when we want to wrap the result into either. In this case, we want to wrap it into validated NEL. So you can use validated catch NEL. That's basically going to allow you to put any suspended effect inside, run it, and automatically wrap the result into validated NEL, right? So the result can be a successful value. In that case, it's going to be a valid containing the value. Otherwise, it's going to be the actual non-empty list containing the error on the left side, because we are mapping any possible exceptions on the left side. We are mapping them to a strongly typed domain, error domain that we want to use, like in this case, speaker not found. And we have the same for load events. We have a list of event IDs in this case, so it's going to return maybe an invalid IDs error or the actual list of events if it was able to retrieve them. So you can validate a catch NEL, put your network wire inside. So it's going to lift the result into valid with the list of events if it's correct, or invalid with the list of errors in case there was any error. In this case, it's going to have a single element. And then you can go like, okay, I'm going to use validated tuple n to run both computations, and that's going to require an error accumulator, which you can create this way. So the error accumulator is like an accumulation strategy for your errors. So and we do that using this instance of non-empty list for the error data type. Okay, so you pass the error accumulator, you pass both computations that you want to run independently, and that's automatically going to give you either a tuple. Sorry, it's going to be a valid containing a tuple of all the successful results if it's correct, if all of them are correct. But if there are any errors, you will get an invalid containing a non-empty list of all the errors. So this is just an example, so you can see the validated NEL is probably the good pick or the right pick when you are going for error accumulation instead of failing fast, because you have non-dependent computations, okay? When you have dependent computations, this is not possible because you cannot really keep computing over your data if the previous computation failed, okay? So you always forward the initial error right until the end. Okay, so, well, so we have means for encoding sequential and parallel or non-dependent computations, and you can imagine that any logics we can have in Android or any programs out there are ultimately a composition of the two. So it's always like sequential and also many times parallel or independent computations. So in that sense, we kind of have like all the tools we might probably need for writing any logics in Android, any pure logics, because we can use them in combination with suspend, as you've been seeing in this snippet. So as soon as you flag as long as you flag your effects as suspend, you will be sure that the compiler will not allow you to call them from anywhere, and you are going to have this requirement calling up the call stack, and the need for providing this runtime for consuming the program. But what happens if we want to use threading or concurrency? Because we've not said anything about that. These data types are eager. They are running their code as soon as you create them. But what happens if you want to run the code in a different thread, a different coroutine context, or even parallelized requests or things like that? That is where the ArrowFX coroutines library comes into play. This is like the library Arrow provides for effects, okay, for working with effects. So all the stuff regarding effects is going to fall into this library. And it's basically like a bunch of operators, of functional operators that work over suspend. Okay, so all the operators expect suspended computations because they are meant for running suspended effects. So you will see that all these operators are expecting suspended lambdas to be passed to them. And these operators are all also suspended, right? They are also defined as suspend functions because we don't really want anybody to be able to call them if it's not for running effects. So we cannot allow anybody to call them from anywhere, but only from a context or a runtime, as we've been saying, that is prepared to run suspended programs. So it also provides collaborative cancellation. All the operators you are going to see here, and also the ones that we are not showcasing today, are automatically supporting cancellation by themselves. So as soon as the parent scope or the parent coroutine gets canceled, they will check for cancellation and cancel themselves and their children jobs or their child tasks. So all that is going to work automatically for you. The environment is, we said a couple of words about the environment, and it's basically provided by ROFX coroutines. That's why I am mentioning it here again. But as we said, it gives you the ability to pick the execution strategy. So in case you are going for the environment, you have functions to run the program synchronously. So it's going to be blocking asynchronously. So you can put it in there, your suspended program, and then you have lambdas for the error and the successful sites. And also the unsafe run async cancelable strategy, the asynchronous strategy that is cancelable. That's going to return a disposable that you can invoke from anywhere to cancel the execution of your call stack, right? And the environment is an actual interface, so you can implement it in different ways. If you want to provide or support your own runtime for Arrow, it's possible for you to do it using that. But as I said, the environment will be deprecated most likely for CO12 because we are going to provide the direct integration with Kotlin X coroutine, so you will be able to use the coroutine scope and the structured concurrency for driving cancellation. So you can use the coroutine builders from Kotlin X coroutines for creating this environment instead of, or this runtime for your suspended program instead of the environment from Arrow, okay? Some operators of ROFS coroutines. Evalon is basically an operator for evaluating something in a different coroutine context and getting back to the original one automatically. So you can imagine you can put any suspended effects in there. For example, here we are evaluating on the IO pool this effect that uses either catch for going to network and capturing any potential exceptions thrown into either left or the successful value into either right, and then we map the potential exceptions in case it failed to some strong domain error type, right? So the result is going to be either of these error or a list of the actual talks. So in this sense, we can use evalon to pick any context to evaluate our effect, our suspended effect in there, and you can put any other operators from ROFX coroutines in there because all of them are suspended, as we've been saying. Okay, this is getting replaced by with context whenever we provide this integration with Kotlin X coroutines because it makes a lot of sense. I mean, both of them are basically doing the same thing, so this is not going to be needed anymore. But in case you are still on 0.11, which is most of the people already, because that's the latest release, stable release we have, you have eval on, okay, for doing this. For parallelizing requests, there is parmapen or partupled n, so it basically allows you to run n suspended effects parallelly or multiple suspended effects parallelly. So in this case, for example, we are parallelizing a couple of effects like operation 1 and operation 2, which are explicitly lifted as suspended functions with this suspend constructor, which is part of the standard library in Kotlin. So that's a way you have for converting a standard function into a suspended one. Let's imagine these two are not suspended functions for any reason. So you lift them into suspend, you make them suspended and run them into Parma. If the functions are suspended, so if the effects are suspended already, you don't really need to lift them or anything like that. Just pass them to Parma and go ahead. And you basically get all results as the inputs or the arguments for this callback lambda you get, where you can compose, for example, a model out of all the results or anything like that. So basically the result of parmap is going to be the result of this block. So this is really, really, really handy because you can parallelize many different operations. This is only parallelizing 2 of them, but it can be many more. And it allows you to do this pattern of awaiting for all the results. This is basically using async and await, the way you can do the same thing with calling as coroutines under the hood. That's what it's going to do, starting on 0.12. So it's going to be more like an alias, one for the other. Parmap is more like the naming functional people is used to. So for now, we are going to keep it, but they are going to be basically the same, right? So you could represent this using calling as coroutines, using async for each one of the asynchronous tasks there, or each one of the suspended effects there, and then await for all of them, for awaiting for all the results, and compose the event, in this case, with all the results. There is part-tupled n, which is more like inline, because it allows you to basically call it in this kind of like inline style, and it gives you the results as a tuple. Okay, so it's something you can use, for example, along with destructuring, so you can assign each one of these elements in the tuple to a different variable, in a single line or things like that. So you can do the same thing you did with parmap n. There is this part-tupled n variant, which is just the same. So how does it work for cancellation? Well, as we said, all the operators check for cancellation by themselves. So if the parent gets canceled, if the parent coroutine here gets canceled, or running this suspend function gets canceled, the parmap n gets canceled, and also all the children get canceled at the same time. Okay, so there's always this implicit parent-to-child relation when we are working with cancellation. In the case one of the children fails, the other ones are also canceled. This happens because this pattern is about the fact of gathering all results to create like an overall composed thing in the end, or composed model in the end. So you kind of like need all results succeeding. So as soon as one of them fails, parmap n or part-tupled n automatically cancels the other jobs. Okay, that's obviously something you can bypass. If you don't really want to rely on this automatic cancellation whenever one child dies or fails, meaning it throws, you can, for example, handle errors within each one of the computations. If you handle your errors here using either catch or something, this is never going to throw because you are capturing all the errors, and also here. So in that sense, the operations always succeed for parmap, and you can bypass that automatic cancellation in case you want to do manually, because you are interested only on some of the results in case some other results fail or whatever. That's nice when you have a number of suspended effects that you are aware of. Like, for example, you have 3, so you put parmap n and you put the 3 effects right there. But what happens if you have a list of elements and you want, so it's like a dynamic amount of elements and you want to run an effect for each one of them, but all of them in parallel, and wait for all the results in the end in the same way we were doing with parmap. There is part traverse for that. So part traverse allows you to take a list of, for example, of IDs in this case, and then you part traverse over it. You have the chance to provide a context, for a coroutine context, and you can run one, an effect for each one of those values, all of them in parallel. So in this case, you will be loading the event all the events by their IDs, all of them in parallel, and wait for results in the end. The result of this is a typo. I will show here the result type that is going to be a list of events in this case. Okay, the result of part traverse in this case. That's for a list of elements where you want to run an effect for each one. But sometimes you already have like a list of effects, right? Like a list of suspended functions. And in this case, you can just part sequence, and that's automatically going to run all of them in parallel and gather results in the end. All these operators provide you the chance of omitting the dispatcher or the coroutine context. So it's always going to run in the default one by default, the actual dispatchers.default from calling as coroutines. And but you can also pass one explicitly, as we are doing here. Okay. What else? There are also operators. I mean, I'm talking about a lot of different operators in arrow, effects, coroutine, but you can imagine there are many more. There's not going to be time for all of them. But there is the chance also for erasing effects or suspended effects. So you kind of keep the winner and cancel all the losers. So you provide a bunch of different suspended effects, and you need to fold over the result, because that gives you a data type that you need to fold over, because you never know if it's going to be which one is going to be the winner. You don't know if it's going to be the first one, the second one, or the third one. So you provide lambdas for all of them with fold. And the cool point of this is that it keeps the result of the winner. So you keep the result of the winner, and the rest of the the losers are cancelled automatically, okay, by raise n, the raise n operator. Again, it automatically checks for cancellation. So if the parent coroutine gets cancelled, raise n gets cancelled, all the children get cancelled. And the same for all the operators we've been seeing until now, okay? That's the same for all of them. So you can see how cancellation is very simple in the world of these functional operators. It's not convoluted at all, because it's always from parent to children, and if a children fails, you cancel the others. So it's like the same thing for all the operators, and that makes it much easier to reason about, because sometimes in the world of Kotlin X coroutines, it's not that easy to use a structured concurrency. You know that there are like a lot of gotchas when you're using coroutine scopes, supervisor jobs, depending on where you install it, it does something or something else. So a lot of knowledge overhead you need to have. And in the case of functional programming, since we really want to achieve certainty and being deterministic, we wanted to pick like a more coherent cancellation strategy for all the different operators we provide. So you don't need to remember, depending on the use case, what you need to do, right? A use case for races in Android, for example, could be binding a task by the activity lifecycle. So you get it automatically canceled when the activity gets destroyed. So you can be creative and, for example, do something like this. You can use a lifecycle observer for along with the suspend coroutine from the standard library. So you can wrap your observer call into a coroutine, and you are gonna continue the suspended job that is calling this method only when you get an on-destroy signal in the activity or an on-destroy event in the activity. So you are basically suspending the execution of this task until the activity gets destroyed. So that's one of the jobs. We are going to have a coroutine that gets suspended until the activity gets destroyed. We can basically raise that against our long-running job that is also a suspended computation for loading, I don't know, an integer value in this case, but you can imagine it could be a more meaningful data, like a list of users or whatever, to render on a screen. So in your activity, you could basically raise n both tasks. So if the on-destroy happens or takes place first, it will automatically cancel the other one, my long-running task. So I'm effectively bounding my long-running task by the lifecycle of the activity doing this, because if it gets destroyed first, it will cancel my long-running task in that case. If it's this one, the one that completes first, it will cancel the one that is awaiting for destroy, which is totally fine. Okay? So races have different possible or potential use cases. It depends on how imaginative or creative you want to be, or you can be on how to use it. That is only an example that we could use in Android. For repeating or retrying suspended jobs, there is retry or repeat. So for example, retry, you have the chance to pass a policy to it, and I'm going to show you in a second how to build and fit any suspended effect in there. To create the policy, you have a very powerful and reusable and composable DSL, like the schedule one. So for example, you can create a schedule that is exponential for an exponential backoff that starts at 10 milliseconds, and I think it has an implicit growth factor of 2, but you can pass an explicit one if you want to. So it's going to be an exponential backoff starting on 10 milliseconds that will keep growing while the output stays under 60 seconds, and then you're going to recurse up to 100 times, one every 60 seconds, for example. So it's a complex policy that you can create that returns an instance of a schedule that you can basically use it with retry to retry any suspended effect that you want to feed in there. So this is really cool because you can inject it. You can generate it, your policy, and inject it everywhere. So if you have a bunch of network requests or, I don't know, database queries or whatever side effects in your system and you want to reuse the same retrying policy, I think it's a really good practice, okay? Because you can inject this schedule and use it everywhere for all your suspended tasks that you want to apply the same kind of retrying policies to. There is also repeat, because the retry keeps retrying meanwhile the effect throws. It keeps retrying it as long as the policy is not over or it doesn't succeed. And there is also the opposite one, which is repeat. Repeat keeps repeating it even if it succeeds. It keeps repeating, but the syntax is the same one. You pass it a policy, so it keeps repeating until the policy is over, or until it throws, okay? As soon as it throws, it stops repeating it. So a couple of operators there, retry and repeat, but you can see how powerful they are, right? The cool point, again, is that they are expecting any suspended effect in the block. So you can use any other arrow operators that are suspended, any other arrow effects operators in there. For error handling, you can imagine that as long as you are using suspend and you're using either or validated, you can put your either catch or your validated catch or your validated catch null at any level of your architecture, depending on how granular you want to be with your error handling, right? Because you can install smaller error handlers per layer, or I don't know, a global one for a bunch of layers together. It depends a little bit on your architecture design or how you want to do it. But given they are expecting suspended code in there, you can basically put them at any level you feel appropriate, regardless of the operators you fit inside. Okay, so it's like very coherent. About the streams and functional reactive programming, well, you know that we are very used to streams. That's probably a long story, so just a couple of slides before finishing, because I think it's probably already quite a lot. But yeah, we also have streams in Arrow. Until now, I mean, we call them the functional streams because we want them to be able to evaluate functional effects, meaning by that we want them to support all the functional arrow effects operators we provide in the library. So we want the stream to be able to evaluate an effect using any of these operators like parmap or whatever, arrays or whatever operator from the ones we've seen, and emit the result over the stream, right? And then keep computing over it using the stream operators and all that. So in that sense, the data type needs to support that, all the RFS coroutines operators, so we can use it functionally and obviously allow things like declarative programming, call the streams, composition, and all that. We had an arrow stream that we still have in 0.11 that we are deprecating, that is basically going to be replaced by flow, because we decided that it doesn't really make a lot of sense to provide a separate data type when flow is really, really extended already in a lot of code bases. So it's probably smarter to bring support for flow, and instead of providing a different data type, keep using flow and add all our functional operators on top of it. So we are going to do that. We are going to take all the operators we had, but port them to be extension functions over flow, defined over flows. So you can also work with flow in a functional way, right? And use both libraries together on integration seamlessly. That's going to come in 0.12, if I'm not mistaken. So in the upcoming versions, for now, if you're using Arrow and you are using streams, you know that the stream data type provides the ability to evaluate effects, as you see here. So you can put any suspended effects in there containing any of the arrow effects operators, as we've been seeing today. You have means for recovering from errors. There is effect map, for example, for chaining another effect afterwards, map, all that kind of stuff. And then you have the terminal operators for consuming it, which are suspended. So you can see a big similarity here with flow if you're used to, right? You have collecting flow that is suspended. And because you shouldn't really consume a stream if it's not from a place that is prepared to run suspended effects, or in other words, to run side effects, because at that point you are consuming the pure program. At that point, you are effectively applying and running all the side effects. Before that point, you're safe. Everything is pure. Everything is declarative. Its code is awaiting to be executed or to be consumed, right? So again, we see this concern separation really clearly. We have our in-memory program, which is like composed of all these operators. In the case of arrow stream until 0.11, it was like this until here. All that is called and declarative and waiting for you to consume it, and then you decide what or which terminal operator to use to finally or to ultimately consume the stream, right? What else? Well, if you get an error in your effect, because you can always get an exception thrown, that's going to be lifted into the stream so you can recover. Basically, it's going to be represented into the stream data type, so you can use your recover methods. In this case, they are called handle error with, but you can think about this more like the standard recovery errors, recovery operators that you have in other libraries like RxJava, for example, to kind of get back to the happy path when you get an error. So yeah, I mean, there's much more than this. That's only like a very simple subset of the operators you got there, but there are things, there are support, other features for, supporting things like scoping the usage of a resource across the life cycle of a stream. So you get access to that resource all the time over the stream, and then when the stream terminates, it makes sure that it's not leaking, so it closes that resource, releases or disposes that resource in the end. So that's really cool to work with any kind of resources like databases or WebSockets or files or whatever that you want to close in the end after using them, so you don't leak. But also things for running streams concurrently, parallelly, things for integrating streams with a schedule, so you can also repeat and retry using all that kind of repeating complexity or logics we've been explaining, or operators we've been explaining today, also along with streams and much more. Also races and more. All that is going to be supported over Flow, or at least all the relevant operators, because many times, as I was saying, Flow already supports them with a different name sometimes. So obviously in those cases, we are not going to duplicate them or anything. But we are going to add all the functional operators on top of the Flow APIs already, or at least all the ones that make sense. So you can use both libraries together on integration without any problem. So that's it. Sorry, because it was a quite long talk. I thought I had asked as much as I needed, but it looks like I need to ask a few more slides to make it a little bit less rushy. But thank you very much for being here. I want to say something else before the organizers take it over, and it's that we have a course for explaining functional programming from 0 to 100. So it's like a fully fledged functional programming in Kotlin course using Arrow, not constrained to Android, but for any Kotlin platform. So that's also valid for backend. And that's happening starting next week on the 19th. So we only have a few slots left, but I definitely recommend it because it's a 4 days long course that is really, 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 really carefully designed. I'm going to be the teacher for all the lessons. So it's 4 days, 4 hours a day, where we go over all the functional concepts one by one with theory and exercises, and we have time for any sort of discussions on everything. So it's totally recommended. You have the link there, and that's pretty much it. I will share the slides on Twitter also. You have my Twitter there. Thank you very much.
Thank you. And I attended your workshop on function on Android a few months ago.
Oh, nice.
It was really cool. So definitely go to check all the other courses that 47 Degrees done, especially the one from Jorge. Cool. I think we have a few questions. There you go.
Okay.
Can you see them?
What is missing for 1.0 release of Arrow? Okay. I think the biggest deal in there is the Kotlin IR, the new Kotlin IR that was released with 1.4, but it's still not solid or stable. So until the new Kotlin IR is completely stable, we depend a lot on that, I'm afraid, because there is Arrow Meta, which is going to provide a lot of utilities using compiler plugins, and that's definitely depending on this new IR. I need to double check if that's still in the roadmap for 1.0, or maybe we are pushing it further. So I'm not gonna I'm not gonna say take this with a grain of salt, okay? Because I'm not completely sure. But that's a big dependency we have, and if it's not for 1.0, it's gonna be for 1.01 or something. But we'll need it. What else? We are in a big refactor to remove a lot of complexity from Arrow regarding type classes and higher kinds, because we want to make it much more accessible. So you can use Arrow more like only thinking about the data types and the operators on the data types instead of knowing like functional programming in depth and all that kind of sometimes too high level of abstraction concepts. So in that sense, there is a big refactor ongoing that needs to happen before that. Also, porting the streams to use Flow instead. So a few things that are happening there. If you want a date, I don't have a date, but probably I think the aim is most likely like first half of the year to be done with everything. But again, take that with a grain of salt because there's a lot of development under works right now. Another question, my Android app is full of side effects. I want to add to start adding FP to it. How I start? Okay, great question. In my opinion, the best way to start is flagging your effects as suspend. So I'm not sure what's your level of integration of Kotlin coroutines already in your app. Hopefully you already have that up and running. So in that sense, you are already using suspend. So it's more about, for example, going to the leaf nodes of your call stack, like all those network queries and database queries, and transform those into suspended calls instead. And then you can start using data types like either, for example, for the computation stat that work with that data. Like, for example, if it's a network request, you make it suspended and then you wrap it into either catch. And there you go, you are already using kind of functional programming somehow in that sense. You are using a functional data type, you are wrapping your request. You can use map left for all the error mappers, which is also really common and probably you're already doing, but using standard mappers. So you can use it within map left. So my recommendation is to do it like probably per feature, to not try to face very, very deep refactors only by yourself, because that's not going to work. But it's always super important to have more people on the team with this knowledge, because otherwise it's a battle that you need to fight alone, which is almost impossible most of the time, because you're learning the concepts at the same time. So it's almost impossible for you to support and give good explanations about everything to your teammates and at the same time learn everything. So I think it's totally recommended if you can get more people supporting you with this knowledge. In that sense, we obviously offer courses and all that in the academy. So we are always open for talking about agreements between companies or things like that. What else? Another thing is not serializable. How can I have the left and right side approach in a seal class and also make the data classes in that seal class serializable too? I think you need, I will need to think a little bit about this, but I don't really think you want to serialize like the whole thing. You don't want to serialize the either containing the data. So left with the error or right with the actual data. What you want to serialize is the successful data when you get it. So probably you need to refactor a little bit your code in that sense. So you don't need to, because you don't want to serialize the whole structure the same way you will not serialize option or anything like that. Maybe you need to redesign your code a little bit in that sense. I'm not sure if you say maybe for passing data between screens on the intents using bundles or things like that. Depends a little bit on the use case, I guess. Am I seeing a nested lambda with coroutines? Isn't that callbacks? Well, I don't know what you're referring to exactly here, to be honest. I don't know. Maybe you want to ping me later on in Twitter or the Kotlin Lang Slack group. That's probably going to be easier if we have a conversation there, because I'm not sure what you're referring to exactly. Sorry. The final question, so I don't leave any any questions left. Since either is now our suspended friend, does IO still have a place? No, I mean, that's actually the point. For the people that is not familiar, we had IO before that got deprecated already, and it's a data type that is meant for wrapping suspended effects, for making them pure. So what you do by wrapping your suspended effect into IO is effectively deferring it. So it's becomes more like a description of an effect than the actual effect. But in that sense, we are replacing IO with suspend. So suspend is the keyword now that takes care of your side effects. It's flagging them so they can become compile time safe. The compiler is aware of them because it's a keyword in the language that is primitive. It's a primitive keyword supported by the compiler, so it already knows what it is and all that. So we can ensure that we have the same guarantees we could ensure with IO by using suspend. So it's more like replacing one with the other. And if you try to start migrating your code base from IO to suspend, you'll see how it becomes much simpler because you effectively remove one of the wrappers over your data. So you don't need to start explicitly wrapping or unwrapping anymore. You are already working over the inner context or the inner value when you move towards a suspend style. So thanks for your talk. Question about your training course during the 4 days. What is the percentage of practice on functional programming? It's 4 days, 4 hours. This time is for the European time. So it's going to be in the mornings, starting at 9 every day. And the percentage of practice, I'm not sure if you refer to the experience you need to have. In that case, it's beginner. So you can go, if you only know Kotlin, but you don't know about functional, that's the best course you could do, probably, because we start from the very beginning. And if you mean how much we use it in practice, we have exercises for each one of the lessons also. So all the concepts, we put them into practice. So I hope it's very rewarding for all the people doing it. And that's it. Thank you very much to everyone and to the organization for letting me be here today.
Thanks to you for this always very interesting talk. Thanks so much.